Everybody, hello, welcome. Today we are going to talk about machining on the edge, smart and sustainable machining. Another word for smart is intelligent, and another word for sustainable is durable. And that's what we are going to talk a bit about today. If we want to do in an intelligent way, in a smart way machining, and if we want to do it in a sustainable manner, in a durable manner, a very interesting tool we have to achieve that is so-called compensation techniques. And that is what I want to talk a bit today with you about, compensation techniques. What do we mean with compensation techniques, and how do they help us to achieve smart and sustainable machining processes? And as always in these events, I'm of course not alone. I'm just the one having the pleasure of talking about these things with you. But of course my colleagues are there, like always, to support, to run the show behind the scenes and to make all of this possible. Now, sustainable machining, as I said, it's a bit on the edge. It's fun, it's also a bit dangerous. And smart machining, one way of defining smart machining is to achieve that an equilibrium is found between all the variables that influence the machining process. It's one way of describing it. I don't know if it clarifies it, but hopefully during this presentation it will. As always, when we discuss these things, centrally I have the machinability model where we say, okay, where we try to describe machining as a physical process, which basically it is. It is a physical process where I deform material, and I deform it so much that the material shears off and is evacuated under the form of ships. That's the description of a machining process, and doing that means that there are quite a lot of physical phenomena taking place during machining. Mechanical ones and thermal ones, and you have tribological effects and so on. And machining is about understanding those, understanding the variables that influence those things, and most important perhaps, understand how to connect those variables in such a way that the main objective of a machining process is achieved. And in working with that, after a while, people of course ask themselves the question, okay, did I do a good job? Did I manage to bring all the variables in balance so that the machining process is leading to the wanted result? And the wanted result is a correctly finished workpiece in the predestinated cost and in the predestinated time for it. That's what we try to achieve with machining. And knowing that, I always say, ask people, the people standing at the machine tool, they have a feeling for the process, and they can tell you. And if you want to have a little bit more of an objective way, look at cutting tools. Look at used cutting edges and they will tell you. Used cutting edges tell a story if you want to listen. It's as simple as that. And that means that we can say, okay, machining, if we try to define it as a physical process with the different chapters in it, the mechanical phenomena and the thermal phenomena and so on, it's about equilibrium. It's about finding balance. It's about making sure that all things are working, working together and not working opposite to each other. And that is the target here from a scientific perspective. That is what we want to achieve, equilibrium. And if we have that, once again, you can see at cutting tools after a while, they tell you the story of how well you did. In this edition, in this episode, again, there's no mathematics. All the machining mathematics I left out, because in modern times we don't have to worry too much anymore about mathematics. We have the modern ways of working with mathematics. We have software, we have things like Seco Suggest. that do all the mathematics for us. Our role today in modern times is the role of interpreter. If results come out, if figures come out, we have to think, we have to use the figures in an intelligent manner. That's the role of people in the modern thing. And if we talk about compensation, so this episode is about compensation techniques to achieve smart and sustainable machining. Now, compensation, and this is perhaps more a philosophical definition than a technical definition, but compensation means that if you have two possible scenarios, if you have two possible situations, that you try to improve by exchanging things between the two possibilities and create kind of a new situation which is an improvement. And it leaves the both original scenarios on a level that is still acceptable. So it's one could kind of say you take two scenarios, you compare them, you take the best of two worlds and you create a new situation. And that is what we refer to as compensation principles. If I use an example that for sure you will all understand, if you work for a company, you are compensated with a salary for the work you do for the company. And in the end, the company is happy and you are happy. That is compensation principle. And we can apply that in technical situations also. And talking about technical situations, soon we have a webinar on high feed or dynamic milling. What is best? And if you start thinking on that, and I would like to invite you all to participate or to listen into this webinar. It's very interesting, because here we have very typical two scenarios, and we compare, and we have to try to find the best possible. That is compensation principles in practice. That's applied compensation principles. And you know, if you talk about compensation principles, it's also about keeping your priorities correct. Because very often when I talk with machining people, what I find out is that machining people are people that fall very easily in love with a cutting tool. And there's nothing wrong with falling in love. But they fall in love with a certain cutting tool, and then they try to use the cutting tool wherever they can. Now, in machining, I think that's not the correct approach. You should first think about the methodology. What is the best possible way of doing something, of achieving the wanted result in machining? And once you thought that seriously over and you came to a decision, then of course comes the next question, which is about, okay, to do this now, what would be the best possible cutting tool serving the purpose I have been thinking about before? But anyway, I should not talk here about this webinar. Once again, if you have some time, join. It's a very interesting thing. It's very important, those things, because today, there's so many possibilities, and it very often leads to confusion. A flashback. A couple of episodes ago, we talked about chip thicknesses, average chip thicknesses, and we defined the chip thickness, and it was a bit of a controversial thing, because we say chip thickness, but basically we do not mean chip thickness. We talk here about the thickness of the material just before it's being deformed by the cutting edge. The thickness of that undeformed material just before it's being cut. To keep it short, we refer to that as the chip thickness. Well, we discussed about that and we talked about that, and we said, okay, chip thickness, the thickness of the undeformed material, is a very important metric in the equation of machinability. Chip thickness is a metric that is an indication for the loads which are acting on a cutting edge. the mechanical loads, the thermal loads, the tribological loads, and so on. And chip thickness and the loads are directly connected. And if for some reason you estimate that the loads are too high, or the mechanical ones, or the thermal, whatever, one of the possibilities is you have to reduce the chip thickness. If you feel you have a cutting tool that can withstand higher loads, you can increase the chip thickness. So chip thickness is something that on the one hand refers to the loads acting on a cutting edge. On the other hand, the chip thickness is related to one of the cutting conditions, namely the feed. So depending on the operation you have, depending on the tool you have, depending on the loads which can be allowed on the cutting edge you selected, the chip thickness bridges towards the feed. It helps you to determine the correct feed. If for some reason you want to reduce the loads, the chip thickness is a bridge that tells you how much you have to reduce the feed. A very nice thing, but milling is a bit complicated because milling is an operation where the chip thickness, the thickness of the undeformed material just before it's being cut, is changing all the time. And then we end up with, how do we handle this? And today, with all the computers we have, it's lesser a problem than it was in the past. But anyway, it's still there from a practical perspective, that in a workshop, how do we, if we observe certain loads and negative consequences, and if we know the feed which is programmed into the machine, how do we handle the bridge there? And to make it practical, we introduce something which is called the average chip thickness. And we define average chip thickness as the thickness of a theoretical chip with the same surface as the real one, with the same length as the real one. So basically we have the same time in cut and we have the same average loads acting on a cutting edge. The thickness of such a theoretical thing, that is what we refer to as the average chip thickness. And we also discussed there that chip thickness, average chip thickness in case of milling, there are variables that are influencing that. One variable is the diameter of a milling cutter. The other variable is the radial depth of cut. Most of the time we bring the two together and we talk about the ratio radial depth of cut to diameter of the milling cutter. We also learned in that episode that the cutting edge angle is a variable influencing the relation between average chip thickness and real chip thickness. And we learned there also that the milling cutter positioning, how you position a milling cutter compared to the workpiece, compared to the application you want to do. So here we have a situation. We talk about average chip thickness, which is a simplification of reality, but to make life doable from a practical perspective in a workshop. So we have something called average chip thickness, and we work with that. And sometimes we decide to increase, sometimes we decide to reduce. And doing that, or for making it possible, we need to know the variables influencing that average chip thickness, and that are radial depth of cut, diameter, cutting edge angle, and cutter positioning, miller cutting positioning. We talked about that. I'm going to come back to it directly. Another flashback, and here I talk about the session of previous month. There we talked about thermodynamics, applied thermodynamics during machining. And we discussed there about that machining is a situation, is a process where heat is generated. That heat spreads out in a workpiece, in the ship and in a cutting tool, and leads to increased temperatures. And those temperatures we want to keep under control, because if the temperature in a workpiece increases too much, I start to have issues with quality, because the workpiece is perhaps expanding, deforming, the material structure is changing, all things which are most of the time unacceptable. I want to keep the temperature in my cutting edge under control, because if temperatures in cutting edges increase too much, the cutting material loses its ability to machine, to cut. And as a consequence of those two statements, we said we have to look on machining in such a way that we try to manage to put the heat in the ships. That very simple principle is we refer to it as applied thermodynamics in machining. And again, we learned while we were discussing that last month that milling is a bit of a complicated thing, because in milling the heat which is generated is not constant in time. As a milling cutter is turning around and the workpiece is moving towards the milling cutter, part of the time cutting edges are not cutting, so no heat is generated. Part of the time cutting edges are cutting and heat is generated. That means that temperatures in cutting edges, in case of a milling application, go up and down. So I don't have a constant heat generation, hence I don't have a constant temperature on the cutting edges, which complicates things a bit in this thermodynamic thinking. Last episode, we say, okay, now there are two possible situations, and it's depending on the radial depth of cut compared to the diameter of a milling cutter. And I take here a bit to the two extreme situations. You can use a milling cutter for slot milling, the situation to the left, where you have the maximum time in cut compared to the total milling time. Half of the time the cutting edges are in contact, are cutting, heat is generated, temperatures goes up. And the opposite is side milling, where only a limited part of the milling cutter is cutting. So you have contour milling, that type of stuff. And here we see that the time where cutting edges are in cut, heat is generated, temperatures goes up, is rather low compared to the total machining time, milling time. That means if I try to visualize heat generation and temperature build-up, and I have a situation where, in case of slot milling, half of the milling cutter is cutting, that we see that the temperature, part of the time is going up while the cutting edge is cutting, part of the time the temperature goes down when the cutting edge is not cutting, but it builds rather fast up. Rather fast, we reach rather high temperatures. Opposite to side milling, where the time actually cutting is rather limited. We see that also here temperatures over time are building up, but not so fast. And we all by sentiment feel that the temperature can be too high. The red zone in the picture here, the temperature in the cutting edge gets too high, the cutting material is softening, the cutting material loses its wear resistance, the cutting material starts to deform, and cutting becomes rather difficult, or tool life is getting rather short. That is rather obvious, but the blue zone in the picture here also says that it can be that the temperature stays too low. Never forget that nowadays cutting materials are sintered materials. You have hard particles, carbides most of the time, which are connected with a binder material. And normally that's a very stiff structure. That is a rather fragile structure, rather breakable structure. To give that structure toughness, we need to increase the temperature a bit to make that the binder materials get softer a bit, and that the grains can move a little bit without directly breaking. So modern cutting materials need a minimum temperature also here to have a reasonable good tool life. Where the problem with too high temperatures is mainly wear-based, the problem with too low temperatures will be mainly fracture-based, that the material breaks, that cracks appear. And you remember last session we talked about this. I'm always interested to see how much people retain from that. Too high temperatures. In case of that I have too fast building up, how do I reduce the maximum temperature in milling? And put it in comments for me. I'm really interested to hear what you have to say about that. What do we do to reduce the maximum temperature? And what do we do to increase the minimum temperature? What do we do if I have a situation where I recognize that the temperature is getting too high, I have to take it down? What do I do if I recognize in a situation that the cutting temperature stays too low and I want to increase it? And the moment you start thinking about that, people, you are thinking about compensation techniques. Temperature is too low. How do I compensate to increase the temperature? Temperature is too high. How do I compensate to reduce the temperature? That's compensation techniques. That's what we are talking about today. Quite a while ago, we also talked about, I didn't exactly call it like that, but today perhaps we should start calling it what it actually is, economic compensation in machining. Some of you perhaps remember from one of the previous episodes that we were talking about economic machining, and that we say it's about costs and it's about productivity. And depending on the situation in which we are, we can say, okay, I want to go for minimum costs, so I can maximize my profit, or I can offer my customers a better price, better mostly interpreted as lower. Or, in other situations where delivery is the issue, I can perhaps offer my customers a better delivery time, a shorter delivery time by increasing my productivity. But we also learned when we were discussing that it seems that the two are different. So I cannot offer my customers, me being a production company now, a machining company, I cannot offer lowest possible price and highest possible productivity, shortest possible delivery time. It's one or the other. And also here we can start thinking in compensating, and we could ask ourselves the question, what could we do to take these two situations, minimum cost on the one hand, maximum productivity, shortest delivery time on the other hand, and start compensating and create a third situation that is both lowest cost and highest productivity. The moment you start talking about that, and for me here we are very close truly to what we could call smart and sustainable machining. How can I do in an intelligent way that I start combining things to create a new situation which is an improvement compared to the previous situations? If you start thinking about that, on the one hand, remember the flashbacks we talked about, chip thicknesses. We also had another thing we already discussed about thermodynamics, applied thermodynamics. Well, if you really start working with that, and in the back of your head, I want from an economical perspective create a better situation, which is a better combination of costs and delivery time. That is the moment we do, and I call this the classic compensation principles in milling. Classic compensation is, as I said, and you see here directly an applied form of it, a table. As I said, nowadays, let's not worry too much about the mathematics and stuff like this. We have modern ways, we have Seco Tools to help us with these things. But here you see, in a visual form, you see here a diagram. And the variables in the table are cutting edge angle, radial depth of cut, diameter of a milling cutter and milling cutter positioning. And you see the blue part, the part to the left in the diagram, is where I have my compensation variables, where I compensate, one could say from a mechanical aspect, with ship thicknesses and stuff. Where I say, okay, if you tell me the situation you have, milling cutter positioning, that type of stuff, and if we know which milling cutter we have, so we know which type of cutting edge we have, so we know what would be a good average ship thickness, that left part in this table, it tells you the feet you should use. So average ship thickness bridges the application and the feet. The right part, the red part, is the same principle, but here based on temperature considerations. If you know the type of application, radial depth of cut, diameter of a milling cutter positioning, what you find in the red part are what is referred to as speed factors. And speed factors I explain directly, but a speed factor in machining is a correction factor to modify, in case of milling, the table feed through the cutting speed to make sure you have the best possible balance. You use the selected tool in the application you have at hand in the best possible way, so you achieve, from an economical perspective, best possible result, costs and delivery time. That's what it's all about. That's traditional compensation. This type of compensation, we do this in milling since 50 years or something. I don't know. I learned this at school, at university 40 years ago. This is traditional compensation techniques. Today there are much more possibilities from a calculation perspective, from the mathematical things, and that makes it possible today, when you use tools like Seco suggests, to do some more advanced compensation. Things we knew before that, okay, there is something, but the mathematics became so complex that we say, okay, we know about it, but let's be quiet about it. Today there's no need anymore to think about how different axial depths of cut related to the tool you use influence the speed factor, influence your table feed. We know that, and here the mechanical and the thermal thing comes together, that there is a relation between average ship thickness and the loads acting on a milling cutter. And if we want to balance the loads, we can derive from an average ship thickness in a certain application another speed factor to make sure things are in balance. And the same story goes for the geometry of a cutting edge. We know that if you create sharper cutting edges, that gives you the possibility to minimize heat generation. On the other hand, you create, from a mechanical perspective, weaker cutting edges, and depending on the type of cutting edge you have, again, you need to correct cutting conditions. So another speed factor can be derived from this. And in the end, it comes all together, the traditional and the more advanced, more modern compensation techniques we knew before about, but we avoided to discuss because the mathematics were rather complex. But today that's not a threshold anymore, once again, as we have things like Seco suggests. And if you take advanced compensation in milling, you can say, okay, the first step is to find out an effective cutting speed. And an effective cutting speed, to have sustainable tool life, constant tool life, you need to take into account workpiece material and the cutting tool features, the carbide grade, the cutting material. That's tradition, that's the nominal approach. And that nominal approach The symbol for it is VCN, N from nominal. You can correct and you can come to an effective cutting speed when you take into account all the speed factors, the correction factors, which are depending from the nominal value, of course, but also from the exact radial depth of cut during the application, the actual depth of cut, the chip thickness, the geometry of a cutting edge, and so on. Once you have that, the second step is to define the effective feet per tooth. Again, to have sustainable tool life, to have constant, controllable, reliable tool life. And that feet per tooth you have in the first phase, the nominal one, depending on workpiece material, and the cutting tool features, in this case the geometry of the tool. But next, you can correct that nominal value and get an effective feet, where again you take into consideration correction factors, speed factors, taking into account the real radial depth of cut, the real diameter of a milling cutter, the wanted average chip thickness, the geometry of the cutting edges, and so on. When you have those two, you can start thinking about the effective rotations per minute, the RPM. An effective RPM is depending on the effective cutting speed, not the nominal one, but the effective one, and the effective milling cutter diameter, the real milling cutter diameter. And once you have that, finally, then we can talk about the effective table feet speed, or the table feet in daily words, which is a function from the effective feet, the effective RPM, and the effective number of teeth. And you know, if you start applying this, that is the moment, and it's typical human, people want to label things, want to give a name to things. And the outcome from this is, depending on the direction you take, that suddenly you find yourself in a situation where, at first sight, the cutting speed is extremely high, if you take all the speed factors into consideration. And then people, to give it a name, they call it high-speed machining. Or you can end up in a situation where suddenly you realize, ooh, this is a very high feet, and that people call then high-feet machining or high-feet milling. And you can end up in a very high RPM, and then people say, oh, this is high RPM machining. But that's just labeling it. It's all applications from one basic principle in machining we are discussing here very briefly, and that is the compensation principle. I want to have a machining operation which is controllable, reliable, that leads me to the wanted result, a correctly finished workpiece at the pre-calculated cost in the pre-calculated time. That is what my customers from my machining company expect from me. And that's what I want to give them. To make that happen, I need to have my machining process under control. And today, that's much more than just saying, okay, I have a steel and I have a carbide grade, so the cutting speed is this. It's more than that. You have to take into considerations, if you really want to be smart, intelligent, so many other factors that will influence that. But you know, nowadays, it doesn't stop there. Because so far we have been talking about the machining process, a physical process where we deform material, shear it off, that we refer to as machining, metal cutting. But that metal cutting is not an island. It does not stand on its own. It happens in a workshop, and if you see this machining operation, and we aim for productivity or we aim for cost, and if possible we want to bring the two together, as I already said. That's one of the basic compensation things we need to do, how to bring these two together. But what we should not forget is that if we see things in a broader perspective, perhaps not every workpiece which is finished after the machining process is correct. Sometimes we lose workpieces because they are not good. Quality is no good. Now, if you produce a workpiece with wrong quality, that of course is going to influence your productivity. And you spend time in producing something that your customer will not accept because it's not good. And that is going to influence your cost factors. On the other hand, if you have a machining operation, in uncontrolled conditions, your machine is now and then going to stand still. Because you need to do something to bring machining back in balance. So not all the time you are producing workpieces. Sometimes the machine tool is standing still and the operator is doing something which is not actually producing workpieces. And what we have to realize that these downtimes also influence your productivity and influence your costs. And this compensation principle that so far we applied to the technological side of machining only, we should extend broader into the organizational side around the machining process. The management, how do I manage all my things around the machining process? And then we end up in we have to give it a name. I call it multidimensional compensation techniques. Compensation techniques where I, on the one hand, focus on the technological side of machining, but on the other hand, and at the same time, on the organizational things around the machining process. And it's all about how do I create a situation so that the machining process can take place in the best possible conditions. So I have it under control, I have a reliable process, I have a process that leads in a predictable way to the wanted results, and then you end up with situations that we say, okay, cutting conditions are also influenced, and I give you here some examples. It's more as an illustration. But then we end up in a situation where we say, okay, cutting conditions, in this case depth of cut, the vertical line, and feed, the horizontal line, are influenced by how reliable want I for the milling cutter to function. How much do I want to avoid unforeseen situations? And that can influence the radial depth of cut. That can influence the milling cutter diameter selection. That is depending, the blue lines in this diagram, by the workpiece material, combined with here the horizontal line is the radial depth of cut, the vertical line is the axial depth of cut. So the axial depth of cut and the radial depth of cut kind of create together a ship with a certain section. And that section, we have to make sure it doesn't get too high, otherwise the milling cutter will start to function in an unreliable way, and that is depending, for instance, by the workpiece material, the blue lines in this visualization, but also the milling cutter diameter. Because bigger milling cutter diameters give us stronger tools, the red lines in this diagram. And there is a relation, again, reliability, big diameters, the horizontal line in this visualization, give you the possibility to go for higher feeds. Because a bigger milling cutter diameter gives you a stronger milling cutter, and a stronger milling cutter in general allows for higher mechanical loads on it before it, for instance, starts to vibrate. And the feed, the vertical line here, and the radial depth of cut, there is a relation between the two, because if you want to go for bigger radial depths of cut, you have to reduce your feed. That's the average ship thickness thinking I referred to a couple of minutes ago. But somewhere, what I try to illustrate here with the blue line, you have to be intelligent, you have to be smart, because from somewhere on, the criterion for reliability is no longer average ship thickness, but maximum ship thickness. The question is, from where does one take over from the other? And you know, if you work with all these things in a smart way, in a user-friendly way, and believe me, user-friendly means that you need to have your iPhone in your hands, you know, and you have to open suggest, and you have to let suggest do all the calculations, because otherwise you are going to be lost. This only became possible today with the help of those things. Before, it was not difficult, but rather time-consuming to do all the iterations and the calculations and stuff. But if you take that step, if you take that calculator in your hand, then suddenly you can modify cutting conditions, depending on the situation you are in, and you can even do that in a time influenced manner, in a dynamic manner. You can nearly create a situation where you put, by selecting tool paths and cutting conditions in an intelligent way, that loads on milling cutters become constant. And if you have constant loads, you will have constant behavior of the milling cutter. And if you have constant, reliable, predictable behavior, you have sustainable machining. And if you do that, the label people gave to this is dynamic. Dynamic machining, dynamic milling, dynamic turning. It's no more or no less applied compensation techniques. The traditional ones, the classic ones, we know since ever, but also the ones we knew before, but we avoided because it was not easy with all the mathematics around it. But that's the smart side of things, you know. That's the intelligent thing. Let the tools designed to do calculations handle that part. That's the calculators, that's the computers. And that makes that sustainable machining, smart machining is getting in reach, because if you can create a situation where the variables, instead of being complementary, are getting supplementary, are adding up to each other instead of replacing each other. Because what I try to say here with the word complementary is that traditional compensation is I take something away from somewhere to add it to something else. That's complementary. Supplementary, I try to define that I take something from my left hand and something from my right hand, add it together and create a situation which is on a higher level. And for me, that's how I see sustainable machining, and I apply it here in a visual way to try to let you understand what I try to express here. What you see is to the left, productivity being prioritized, and here productivity is visualized or is determined by the MRR, the metal removal rate. And metal removal rate is influenced by cutting speed and feet, very clearly. That's the productivity story. To the right, you see the cost factor, at least a simplified form of it, tool cost factor, where tool life is a very important thing. And here the vertical line is feet, like to the left, and the horizontal line is cutting speed. So we see feet and cutting speed, and how you combine the two gives you a certain metal removal rate, productivity, and gives you a certain tool life, hence a lead to cost factors, tool cost factors. And you can increase your metal removal rate, then you need to be able to select feeds and cutting speeds that are one of the two or both higher. That is going to increase your productivity. On the other hand, if you want to increase tool life, you will have to select lower combinations of feed and cutting speed, and then you will have a longer tool life. That leads to lower tool costs. So far, those things are always seen a bit separate. It's one or the other, we say in machining. Make your choice. But we can put things on top of each other and see what we can do to combine things. And here that is what I refer to as my economical compensation. Isn't there a possibility to bring things together? Sorry for this. It seems I shocked the computers with all the calculation they have to do when we talk about smart and sustainable machining. Sorry for this. I hope you stayed a couple of minutes. We restarted the stuff. I was saying, talking about compensation, it's about, in the end, it's about economical compensation. It's about how to bring costs and productivity together. And if I quickly go back to this, I said on the one hand you can focus on productivity, the left side. On the other hand you can focus on costs, the right side. Most of the time traditional machining people say, oh, it's this or it's this, make your choice. But we can try to bring things together in a smart way and see what we can do then. Of course, we need to respect the reality. We cannot do whatever we want. There are limitations. The application window of a machining process is defined by mechanical phenomena, thermal phenomena, tribological phenomena, and we need to make sure we stay in a window where things are under control. But in that window, we can start asking questions, because the blue lines and the red lines, they cross. And at every of these cross points, crossroads, you have a situation where you have a certain combination of cost and productivity. Well under control because you are in the application domain, framed by technological stuff. And now it's not anymore about, pick your pick, go for cost or go for productivity. No, now we are in a much more intelligent situation. Now we can say, okay, let's think about which combination of cost and productivity do I want, is needed. And that's a much more sustainable approach. I mean, this gives you the possibility to think about the future also, not only today. But once again, doing this is if you want to do it in an intelligent way, don't even think about making manual calculations for this, but turn to appropriate help for that, to so-called software. Think on Seco Suggest or similar stuff where you can think in terms from, what can I do? And if I want to do it on a higher level, if I want to put my machining processes on a higher level towards the future, for that you need insight, but you also need calculation power. You need both. That's what I wanted to bring forward today. Now I'm quite sure, because before when I talked about these things, people sometimes say, I had a number of questions before, and now after listening to you, I have even more questions than before. If that is your case, don't worry, because here we are talking about machining on a rather high level. If you want to have a copy of the presentation, that's of course available. Just let me know, put it in comments, let me know where I can send it to. In other words, let me know an email address or something, and I promise you will have them in return. Lots of these things are also dealt with in the technical books we have. We have 5 technical books about machining. I'm not referring here to technical guides, but really technical books where we talk about machining as a process. These compensation principles are also dealt with in those books. If you want to have information on those, if you want to know how you can get your hands on those books, again, don't hesitate. Leave me a message in comments, and I promise you we make sure the information gets your way. We have a little bit of delay with the technical break we had. But anyway, let's see if there are some questions that we can give an answer still today. There is a question, what about solid milling? What about solid milling? I have been talking here about milling in general. And if you look to cutting tools, you have cutting tools where we refer to as an insert system, where the cutting material comes in the form of an insert. An insert we put in a steel milling cutter. That's the concept of the tool we refer to as insert-based insert system. Next to that you have solid carbide, where I would say it's smaller milling cutters, the more complex shaped milling cutters, where the carbide material is used for the cutting edges, but also for the milling cutter body. All is in one. Now the principles I talked about for both are the same. The values will be different. That is one very clear difference, of course. And my personal sentiment also a little bit is that these compensation principles are are more critical in solid carbide milling cutters. Because if you have a system, an insert system milling cutter, where the cutter body is steel, now steel is a more forgiving material if there is somewhere a mechanical overload than carbide. So a solid carbide cutter is I should not make you afraid of it, but it's more critical. You have to know better what you are doing if you work with solid carbide. The expertise of let me put it like this, the principles are the same, but the expertise of the machinist, of the operator, or the engineer, the programmer, when you use solid carbide milling cutters, is yeah, now other people are going to be offended, but it's more critical. I hope that kind of answers the question. Another question, let me read. What about ratio between minimum time and high quality and sustainable tools? Minimum time, high quality. A very interesting question. I would like to invite you to the live event for next month where we are going to talk about machining quality. So I do a nasty thing now. I say I'm not answering the question here. Join us next month for the next session and we are going to talk quite intensively about it. And sustainable tools, yeah. I don't know what to answer about the expression sustainable tools. I don't think tools are an operation, a manufacturing operation being machining, but it can also be welding or sheet forming, whatever manufacturing organization. We should aim for doing it in a sustainable way. And for me, a sustainable way is doing things in a very simplified form now. Sustainable machining, if I say to that, sustainable machining is doing machining in such a way that it fulfills the needs of today, that I produce a correctly finished workpiece, without jeopardizing future needs. That's for me sustainability. And for the rest, you can put as many details as you want, but it's doing things in such a way that the needs of today are fulfilled, and we respect that in the future we still need to be able to do things. If you want to have sustainable machining defined like that, all the elements in the process needs to be very carefully considered or reconsidered. Also the cutting tools. And cutting tools being well considered and selected so they contribute to that the machining process is sustainable, that as far as I'm concerned, you can call that sustainable tools, but I find it a little bit dangerous because a cutting tool can for one application be sustainable, but that doesn't mean necessarily wise. It's for another application also the best choice, the sustainable choice. So be a bit careful with that. I always say if we use the word sustainability, let's be clear. Do we talk sustainability the scientific approach, or do we talk sustainability the marketing approach, if you understand what I try to say with that? One last question. Is there any relation between tools, which one using solid carbide for milling, HRC hardness to... yes, of course. The concept of a solid carbide tool, as I already was saying for the first question, a solid carbide tool, the concept of such a tool is different from the concept of an insert-based tool. As we talk about two different concepts, yeah, how we use the tools must be different. And that goes as far as that even if you take an insert-based tool and a solid carbide tool, the same carbide material, imagine it's the same carbide material and the workpiece material in which you are going to machine is the same. Even if you have that same combination, a solid carbide tool, the cutting speed, the feed will be different than the cutting speed and the feed you use with the insert-based tools. Yes, of course, there is a relation between the tool concept and how you use the tool. And I see questions are continue to come in. One last then for today, and all the other questions I take care afterwards in the comment in the comment chapter related to this episode. The problem an answer. The problem of higher cutting temperature can be slightly reduced by improving heat dissipation during machining, yes, vis-à-vis increasing chip thickness, increasing feet per tooth. Well, this answer comes from Shuhosh. I hope I pronounce it well, because I want to say yes. Allow me to say congratulations. What you say here is a very perfect answer to that question I asked when I was showing that slide. You make me really happy, proud to read what you say here. The other questions, as I said, I'll answer in the comments. We are already a little bit over time. I want to stop here. Again, I would like to remind you the upcoming webinar we have on high feed or dynamic milling. What is the best choice? Where do I use what? And if you look a little bit here in detail, and you see it's a nice illustration of what I said. We first have to think about how are we going to do something? Which system, which method? And only secondary comes, or secondary, that sounds, it's not important, but I don't mean like that. Only when you have reconsidered, seriously considered, how am I going to do something, so the result comes in a sustainable way, and I do it in a smart way, an intelligent way, only then we should focus on, okay, which tool do I need so I fulfill the expectations. Again, if you have time, please join. It's going to be a very interesting one. For me, I stop here. Thank you very much for participating. Today was a rather complex subject. I hope, because here and there I have a feeling I jumped a little bit fast from one corner to another corner. If you want a copy of the presentation, let me know. If you have questions, if you want further clarifications, don't hesitate, put some things in comments. If you want to know about technical literature available around this subject, let me know. We take care of all your requests and make sure that in the best possible, in the shortest possible time, you have answers to your questions. Next time, the last of this season, we are going to put things a little bit together and talk about what is really important in the end, a correctly finished workpiece in the wanted time and at the wanted cost or price. How to achieve that. And we are going to use all the things we have been talking in previous episodes and bring it all together in that one last final statement. How to produce a correctly finished quality, time, cost workpiece. Thank you very much. Looking forward to see you at the next episode.